What a fiasco. Well, welcome back. As I said, this is the final push. All right, we're almost there. Take a deep breath. Christmas is coming. And we got some ground to cover between now and then. So I'm just going to dive in because we've wasted 15 minutes getting the tech to work. Thank you for the suggestion. That's perfect. All right, so the remaining things we're going to do this semester, no new reactions. What we're going to do is talk about how we know what we know in OChem. 3 different, what we're going to call spectroscopic techniques. Spectroscopy in organic chemistry means using light to detect something about a molecule. And in our case, we're going to learn about infrared spectroscopy, which is going to be detecting functional groups in organic molecules by looking at bond vibrations. We're going to talk about nuclear magnetic resonance spectroscopy, which is going to be looking at different kinds of hydrogens and carbons in organic molecules. But today we're talking about mass spectrometry. If you want to anger an analytical chemist, if you want to make them upset, if you want to rage bait them, you say mass spectroscopy. They're just going to go, "Ugh," because they call it mass spectrometry. Nerd emoji with the uplifted finger. Actually, it's mass spectrometry. And the reason is mass spectrometry doesn't really use light and we're not absorbing anything, but we are using an instrument to measure something. So whatever. So we're going to talk about mass spectrometry today, which is how we know molecules have the right molecular weight. Now, this chapter or this section of your text, spectroscopy section A, on mass spectrometry, just barely scratches the surface. There are tons more stuff you can do with mass spectrometry that we're going to talk about today. We have quite a few mass spectrometers in the department. Some of them are pretty simple. Others of them are like almost $1 million instruments that require full-time people to maintain, and we can do awesome things with proteins and proteomics with them. But today we're just going to talk about simple measuring the molecular weight of a molecule. So I've got a bunch of, this section really doesn't lend itself to me drawing too much because I need images that I can't draw. So I'm going to post these notes so that you have access to them so you don't need to worry about drawing this. The basic idea from the earliest kind of mass spectrometry is, first, that charged particles move in a magnetic field. So that's physics. We're not going to learn any physics equations here, but you should have the idea that if you put a charged particle in a magnetic field, it's going to move in a curved path. And its pathway in the magnetic field is going to be determined by 2 things. First, its mass, and then its charge. And so the first thing we need to do to be able to identify neutral organic molecules is give them a charge. Now there's lots of ways to do this. What we're showing you today is only one of them. And this is electron ejection, meaning you gotta make the molecule lose an electron and then it becomes positively charged. This isn't the method that's used a lot today. There are a lot of other methods that are used, but we'll sort of go with this one. The idea is you take your molecule, M, that has a particular mass, you bombard it with a beam of electrons. That repulsion ejects 1 electron from the molecule, and you now end up with a radical cation. This is something that has 1 unpaired electron and 1 positive charge. Where does that electron get ejected from? I mean, the best guess would be from the HOMO, but it's not always that way. And the ejected electron goes somewhere. What you're left with is the radical cation. Then you have some negatively charged plates with slits in them that accelerate the charged particle through the little slit. And then beyond that point, the charged particle goes in a straight line until it encounters a magnetic field. And the magnetic field diverts the pathway of that charged particle. And the charged particle can curve in slightly different directions based on its mass. All of the particles are going to have 1 plus charge, but their masses are going to differ, and so the extent of their movement is going to differ. And from that, in a detector, you can measure these ions and detect what their masses and charges are. And the output that comes from this is called a mass spectrum. On the y-axis of a mass spectrum, you have something that's just intensity or counts or number of observations. That's number of times you see a particular particle. And then on the x-axis, you have not mass, but mass over charge. Now, for our purposes, that's the same thing, because if mass is m and z is charge, and if z equals 1, then m over z equals m, right? We okay with that? So on this axis, you can interpret that as long as you have the assumption that charge equals 1, you can interpret the number on this axis as being the mass of the molecule that you're looking at. Okay, there are questions about that overall? Yeah?
Do you average all of the values?
So why are there multiple peaks, and do you average them? You don't average them, but what do those peaks mean? We are going to talk about that. Yep, what else? Okay. So here is an example of the mass spectrum of methane. Now, all of the images I'm going to show you today are from low resolution mass spectrometers. That is, you look at the mass of methane and you expect it to be 12 for carbon, 1 for each of the hydrogens, 16 overall, 0 significant figures past the decimal point, and that's good enough. In practice, for modern mass spectrometry, we have high resolution techniques that actually allow us to see the difference between carbon and hydrogen and nitrogen and oxygen, and I'll talk about that a little bit later. But let's look at the mass spectrum of methane. It's kind of weird because there's a lot of peaks, okay? If you start at the highest m over z ratio, there's a peak at 17. It's really small. Then there's a large peak at 16. And then there are smaller peaks at 15, 14, 13, and whatever's less than 13. What is it, 12? Something like that, right? 6 or 7. So what do these peaks represent? So there's an arrow here to the tallest peak called the molecular ion peak. That's the one that has the expected mass over charge ratio, or the expected mass of 16. Now, the interesting thing is that mass spectrometers can tell the difference between isotopes of an element. So you know, for example, that from Gen Chem, perhaps 99% of carbons are carbon-12, but a certain percent of carbon, about 1%, is C13, meaning carbon with 1 extra neutron. And then some really small amount is C14, meaning carbon with 2 neutrons. Same thing with hydrogen. 99.99% hydrogens are just proton, but then a small percentage are deuterium with 1 neutron in the nucleus. Same thing with nitrogen. There are higher molecular weight isotopes of nitrogen, higher molecular weight isotopes of oxygen, chlorine, bromine, and so on. This peak at m+1 represents molecules that have 1 extra neutron. For the case of methane, that might be in a C13 isotope, or it might be in a deuterium isotope. Okay? Does that make sense? So you're literally seeing the isotopes that are mixed into your sample based on natural abundance. Now in methane, that peak is going to be small because there's only 5 atoms in methane, so there's not that many ways to have an additional neutron. As your molecule gets bigger and more complicated, there end up being a lot of ways to have 1 or 2 or 3 or 4 extra neutrons. And so with larger molecules, these multiple neutron peaks start to become bigger relative to the molecular ion peak. In the kinds of molecules that I deal with in my lab, the molecular ion peak is actually here, and then the isotope peaks show up here, simply because the molecules I deal with have hundreds upon hundreds of atoms in them, and therefore there's many more ways to have an extra neutron than there are to just have the base isotopes. So what you expect to see in a mass spectrum depends on the size of your molecule. Are there any questions about where this isotope peak comes from? Okay, one interesting thing is that if you have a chlorine or a bromine in your molecule, chlorine and bromine are weird because unlike the other elements that we typically deal with, there's a huge percentage of chlorine and bromine that is not the low mass isotope. So the most abundant isotope of chlorine is 35, Cl35. That's 76%, about 3/4 abundance. But the remaining 25% is Cl37. Meaning that if your molecule had chlorine in it, you would expect to see a peak at M+2, and that peak should be about 25% in height relative to the molecular ion. That represents the 25% of molecules that have Cl37 instead of Cl35. So in a mass spec, if you see something like this, where you see a peak that's +2 away from your tall molecular ion peak, and it's about 25% of the height of that molecular ion peak, that's a dead giveaway that you've got chlorine in your molecule. So this is a clue, gathering pieces of information, it's a clue. Same thing with bromine, except for bromine, the 2 main isotopes are bromine 79 and bromine 81, and their relative abundance is about 1-to-1, about 50-50. So if your molecule contained bromine, you would expect to see a peak at M+2, and you would expect it to be just as tall as your molecular ion peak. And again, that would be a dead giveaway that your molecule has a bromine in it. Okay? All right, so what about these lower mass peaks? 15, 14, 13, 12. What does that represent? And this is something that will occur or not depending on how your mass spectrometer works. In the case of bombardment with a beam of electrons, that's pretty high energy, and the radical cation that you make has lost 1 electron, so that means bonds, a bond at least, is going to be weaker. And so you can actually start to see some of these molecules fall apart and fragment because the radical cation that you make is often not stable. Here's an example of how that happens with methane. Okay? So suppose in the methane radical cation we've lost an electron. That means 1 of the 4 carbon-hydrogen bonds is weak. It's only got 1 electron in it. And so one of the ways this molecule can fragment is we lose a hydrogen atom. Now that's neutral, and what's left behind is CH3+, methyl cation, which should have an M/Z of 15. Okay? So when you see that M over Z of 15 peak right here, that's methane that's lost a hydrogen atom. You can tell that it lost a hydrogen atom and not anything else because mass spectrometry does not detect neutral particles. It only detects charged particles. So everything that shows up here in the fragments has to be charged. All right, so the 15 is probably this methyl cation. The 14 is probably methyl cation loses a hydrogen atom and becomes this radical cation. If that one loses a hydrogen atom, you have this CH cation, and then if the CH cation loses a hydrogen, you have this. Now this is going to look strange, like you were not sure any of this could happen, and you're right, none of that happens in solution at all. This is high energy chemistry that happens in the gas phase, and it happens because you just shot your molecule with a beam of electrons and a bunch of stuff happened. Now, people used to try to interpret the fragmentation patterns in a mass spectrometer. And there's a whole bunch of stuff in spectroscopy section A about interpreting fragmentation patterns. That's not done so much anymore because we have high resolution mass spectrometry and we have other better techniques for assessing the connectivity of the molecule. So I'm going to show you an example of the data so you can have an idea of where this comes from, but I am not going to be asking you to interpret fragmentation patterns. All right? So just to review, this is the 17 is the +1 neutron peak from isotopes. The base peak is often called the monoisotopic peak, meaning there's only one, the most common isotope. And then these are fragments where we've lost an individual hydrogen atom. Let's look at the mass spectrum for hexane. All right. So the molecular weight for hexane is 86. And you can see that peak here, the molecular ion peak. You can see the +1 isotope the +1 add 1 neutron peak. And then you can see a couple of fragments. But interestingly, this molecular ion peak of 86 is not the most abundant peak. And the reason for that is using this, what we're going to call ionization method, the beam of electrons, the hexane molecule has fallen apart. Now you can tell by the masses, perhaps, what the hexane molecule has lost. For example, if we lose a methyl radical and we end up with this cation, that's M minus 15 or 71. So that shows up here, okay? If we lose an ethyl group, that's M minus 29 or 57, and that's actually the most abundant ion we see here. And then if you did the math, you could discover the other possible things, losing 47 or losing 57, depending on which bond in hexane you're going to break. Now, if you did all of that, go ahead.
Is there any way we could tell between like a fragment and just a lighter isotope like oxygen?
Is there any way to tell between a fragment and a lighter isotope, like oxygen 15? I don't know oxygen 15. Does that exist? Just guessing. Get rid of a neutron from oxygen. No, I guess assuming a lighter isotope would exist, you wouldn't be able to tell the difference between a fragment and a lighter isotope. So some people have made a career out of like, okay, we're going to piece together the structure of the molecule based on the fragments that we see. That kind of thing is useful, And in fact, there's a whole field called proteomics, which is based on analyzing fragments of proteins and calculating what the sequence of those proteins must be. But I'll tell you, it's hard to do by hand, and now in modern mass spectrometry, we use computers to help us piece together the fragments. So we won't talk about the fragmentation patterns much more beyond this. And I don't think I've assigned a large number of fragment interpreting patterns in your study guide, and I certainly haven't put any fragment interpreting questions on your problem set. Let's see, I already told you about halides and the +2 peak. Let me give you just an example of this. Here is a simple organic chloride, has this structure. You can see that there are a bunch of fragments. So when you're interpreting mass spec data where there could be fragments, you go to the highest group of peaks that you can see. And the tallest peak in that highest M/Z group of peaks is likely your molecular ion. And then you look for the fragments and the isotopes. In this case, I see a main peak here, which is likely my molecular ion. Then I see M+1 here that's really small. That's the +1 neutron peak. And then I see a +2 neutrons peak that's pretty tall, about 25% of this one. Height ratio is about 3 to 1. And that is the M+2 peak. That corresponds to the 25% of molecules that have chlorine-37 versus the 75% of molecules that have chlorine-35. Now, you don't see that pattern in some of these other fragments. Why not? Presumably they've lost chlorine. Okay, let's look at a bromine molecule. This is sort of the same molecule, but with bromine instead of chlorine. And again, if you zoom in on the highest molecular weight group of peaks, you see 2 peaks in a 1-to-1 ratio. This is the molecular ion peak. This is M+2. The fact that they're in a 1-to-1 ratio tells you, there's probably bromine there. There's nothing else that does that. There's nothing else that gives you a M+2 that's the same height. Okay, questions about that? Yeah, go ahead.
Why is the big base peak so much higher than the molecular ion peak?
Why is the base peak so much higher in intensity, relative abundance, than the molecular ion peak? Probably because the method you're using to ionize the molecule is so destructive that most of the molecule fragments. So really on a mass spec, you're seeing probability or likelihood of things happening. And the fact that this fragment peak is so much higher just means most of the time, the molecule fragments. Now that's true for this ionization method. If you go work in one of our labs and take a mass spec, we never see fragments because the ionization method we use is much more gentle now than it used to be. Excuse me. Okay, others? All right, couple of rules of thumb. You've learned the M+2 rule for looking for chlorines and bromines. A couple other rules of thumb. Now, what I'm going to say here is going to help you answer questions in a study guide and possibly on MCAT or DAT, but it's not going to be that useful in the lab. For the most part in the lab, when we're looking for a molecule, we know what the molecular formula of the molecule should be. We're just verifying that we've made what we say we made. However, there are times when you're looking for something unknown and you kind of want to narrow down the possibilities. Excuse me. So one rule of thumb is that the molecular ion that only has carbon, hydrogen, and oxygen in it has to have an even molecular weight. Now that's if you're only just adding, just to be clear, that's if you're dealing with atomic masses without any decimals, okay? This is 0 significant figures. This is 12, 1, 14 for nitrogen, 16 for oxygen. If the molecule only has carbon, nitrogen, and carbon, hydrogen, and oxygen, the molecular weight has to be even. It just works out that way. In contrast, if you have an odd number of nitrogens, the molecular weight has to be odd. If you have an even number of nitrogens, it could be even. But basically, if somebody gives you an M over Z and it's odd, that's a clue that your molecule might have 1 or 3 or 5 nitrogens, an odd number of nitrogens. I know you're thinking, is that useful? And the answer was, it used to be. It's really no longer useful. But again, there may be questions in the study guide that might have you deal with that. Okay, I have some stuff here about fragmentation patterns for common functional groups, which I wrote down and then immediately stopped caring about. So we're just going to skip that. Okay? Delete it. All right. One thing that's highly useful to you, though, in solving structures of unknown organic compounds, and this doesn't really have to do with interpreting mass spec data, but if you take the Organic Chemistry Lab 353, at some point you're going to be identifying unknowns. And even in this class, you're going to be given some data about an unknown compound, and you're going to have to try to identify what it is. One of the most useful things you can do if you have a molecular formula is calculate how many pi bonds or rings that molecule has to have. That allows you to narrow down the possibilities pretty quickly, and it allows you to draw guesses for what the structure, more efficiently draw guesses for what the structure is that's consistent with the molecular formula. So I want to introduce a concept called degrees of unsaturation or double bond equivalence. The idea here is that every time you introduce a pi bond to a molecule, that takes care of or eliminates 2 hydrogens from the molecule that would have been there in the completely saturated alkane. So at some point in the past, I think, you learned that in general, for a hydrocarbon that's an alkane with no pi bonds, the general formula is CnH2n plus 2. That is, if your molecule is hexane and it's got 6 carbons in it, it has to have 14 hydrogens. 2 times 6 is 12 plus 2 is 14. So compare ethane, which has C2H6, with ethylene, which has a pi bond in it, C2H4. Every pi bond you introduce is 2 hydrogens fewer than the corresponding saturated alkane. Same thing with rings. Look at propane versus cyclopropane, C3H8. That follows the 2n plus 2 pattern. Cyclopropane, C3H6. Every ring you introduce accounts for 2 hydrogens that are missing from the relative to the just acyclic alkane. Why? Well, to get the ring, you have to pop 2 hydrogens off the end and then connect the carbons. Okay? So if you can look at a formula, compare the number of carbons to the number of hydrogens, you can tell whether there's any pi bonds in that molecule or not. So here's an equation. I know you love those. here's an equation, and I'm not going to justify it for you. I've talked about rings and pi bonds. This equation also accounts for the number of nitrogens and halides in the molecule. If you think about it, every halide you put in the molecule takes the place of a hydrogen. So we're subtracting a halide. And then every nitrogen you put in the molecule has to introduce a new proton as well, because nitrogen can be bonded to 3 things. Okay, oxygens you just ignore. Because every time you introduce an oxygen to a molecule, if it's just an OH group with no double bonds, you pull the hydrogen off, the oxygen goes on, and then the oxygen is bonded to a hydrogen. Okay, so this is your equation for calculating the number of degrees of unsaturation or double bond equivalents. The idea is 2 times the number of carbon plus 2 minus the number of hydrogens minus the number of halides plus the number of nitrogens. So C6H6, do the double bond equivalents. You end up with 2 times 6 is 12 plus 2 is 14 minus 6 is 8 divided by 2 is 4. 4 double bond equivalents. This is a benzene ring. You have 1, 2, 3 pi bonds and 1 ring. That's 4 degrees of unsaturation or 4 double bond equivalents. And it turns out that is the only way you can draw a structure that has the formula C6H6. And if you didn't know that, at least calculating the double bond equivalents would give you some ideas of what the structure of the molecule would be. Notice if we replace one of the carbons with a nitrogen, we get C5H5N. Well, let's do the double bond equivalence there. 2 times 5 is 10, plus 2 is 12, minus 5 is 7. Then you add 1 for the nitrogen, that's now 8, divided by 2 is 4. By the way, if you do double bond equivalence and you end up with a decimal, like 1.5, you've done it wrong. And probably you forgot to take account of a hydrogen or of a nitrogen or a halide. Okay, so, and it turns out this is the only way to do C5H5N. 4 double bond equivalents, 3 double bonds in the ring and 1 ring. Okay, are there questions about doing that? At this point, it maybe doesn't seem like it would be that useful, but once you start solving the structures of unknown molecules, it really helps you narrow down the possibilities when you know how many pi bonds or rings the molecule could have. Okay. Anything else we need to say about that? Uh-oh. Oh, no, we are getting audio. That's excellent. Okay, so in the remaining couple of minutes, I want to introduce you to infrared spectroscopy. This is one way we can tell really quickly and very cheaply what kinds of functional groups there are in your organic molecule. And this is something, if you take the 353 organic lab, you will actually do. You will take the IR spectrum of a molecule that you make. So what is infrared? So here's the visible spectrum. Oh my goodness, my son's found some song that some poor soul had made in high school about the electromagnetic spectrum, and it was terrible, but I think it helped them. So anyway, I don't remember where infrared came in, but gamma rays, X-rays, ultraviolet. Anyway, infrared is lower energy than visible light. And it's in the range of wavelengths from 2 to 25 micrometers. We have a weird way of dealing with wavelength in interpreting infrared spectroscopy. For whatever reason, historically, people didn't want to deal with micrometers or microns. They also didn't want to deal in frequency or hertz because those numbers were in the trillions to hundreds of trillions. So they chose something that worked okay, and that is the inverse of wavelength, where wavelength is expressed in centimeters. It's bizarre. I don't know why. But the term we will use for wavelength is called wave number. It's 1 over wavelength, and it's in units of inverse centimeters. And the interesting thing about wave number is it's basically proportional to frequency. So higher wave number means higher frequency, means higher energy of light. That's all you need to know really about that, but understand that wave number is just a weird way of describing wavelength or frequency. You can think of it as how many waves are there per centimeter of space. So 4,000 wave number, 4,000 waves in the centimeter of space. And from that, you can calculate frequency and wavelength. The idea is infrared light is the right energy to excite not electrons jumping from one level to another, but to excite bond vibrations in molecules. You didn't know that was necessarily a thing, and I'm telling it to you now. And when we talk next time, I will show you a bunch of examples of bond vibrations that are excited by infrared light, and we'll learn how to interpret some data. Sorry about the tech troubles. I will see you on Wednesday.